Frictional forces on flat belts, topic 8.5 theory. So this presentation has both wedges and frictional forces on flat belts. This topic is not in our syllabus. So it's topic 8.4, that's not in our syllabus. It's 8 frictional forces on flat belts, topic 8.5, that's part of our discussion. So again, the objective is to determine tension in a belt. That's our objective, not this one. Okay. So first question is, again, that's not part of our discussion. So let's look at the second question. Until now, whenever we had like a pulley system and we have drawn the tension at the ends of the pulley like T1 and T2, we always said that T1 is equal to T2 because we neglected the friction between the belt and the pulley, or the rope and the pulley. If you read the problem statement, you will see that neglect the friction, or it's a frictionless pulley. Those were the words. But now in practical life, there is always friction at the belt and pulley. So T1 is equal to T2. So how do we calculate what is the correct equation in this problem? So in this case, the force is applied at T2. So when force is applied, that results in rotation of the pulley, or the motion or impending motion of the belt relative to the surface of the pulley is in counterclockwise direction. So in this case, T1 value is more than T2. So T2 is more than T1. So T2 is greater than T1. And what's exact value of T2 depends on the angle of contact of the belt with the pulley. So the belt is contacting here with the pulley, and it stops contacting here, and that angle is beta. So T1, and since T2 is greater than T1, the correct equation is T1 is less than T2. So this topic, we are skipping it. It's not what we are discussing here, but yeah, and this is okay. This is fine. This is our course. So whenever in the design of a band brake, so this is called the band brake, where the rotating wheel is and the brakes on the rotating wheel are applied using this lever and this like rope arrangement. So at that time, the tension at one end of the rope is not same as tension at the other end of the rope. So typically the force, the end at which the more force is applied, has higher tension than the other end of the belt, and that we can calculate using this belt analysis concept. So consider a flat belt passing over a fixed curved surface with the total angle of contact equal to beta radians. So remember, this beta here is in radians, not in degrees. So if the angle is given in degrees, so you will find out, you need to convert this into radians by multiplying degrees with pi by 180. Okay, so that will convert into radian. So 1 degree is pi by 180 radian. That's why 360 degrees is 2 pi radian, or 180 degrees is pi radian. If the belt slips or is just about to slip, then T2 must be greater than T1, and the motion resisting the friction forces. Hence, T2 can be calculated using this equation. T2 divided by T1 is equal to e to the power xe, where e means exponential to the power mu beta, where mu is the coefficient of friction between the belt and the drum or the wheel, and beta is angle in radians, and T2 and T1 are tension at both ends of the belt. Okay, so let's and then there is problem solving. We will do that in the next video, but let's look at it one more time. So for this problem, again, the T1 is here, T2 is here. T2 is the tight side because it's being pulled from here, or force is being applied at T2, angle is beta. Then T2 divided by T1 is equal to e to the power mu beta. But if this is reverse, for some, that T1 is pulled, and this is the direction of motion, and if this is angle beta, and this is T2, then the equation will be T1 divided by T2 multiplied by e to the power mu beta. So remember, whatever is the tighter side, or the side at which the force is being applied, that's on the numerator. The other one is in the denominator, and equal to exponential to the power mu multiplied by beta. Once again, beta is radians. It's not degrees. So in the next video, we will apply this concept and we'll solve some problem. Thank you.